Hi, my name is Virat Shezwalkar, and I will be talking about our work manipulating the Byzantine, optimizing model poisoning attacks and defenses for federated learning. This is a joint work with my advisor Amiru Mansadra at University of Massachusetts Amherst. Federated learning allows mutually untrusting clients to collaborate via an untrusted FL server called central server and train a joint global model on all of the client's local data. Such global model generally outperforms the models trained on any individual client's local data. In any given FL round, the server broadcasts the most recent global model to a subset of FL clients. These clients compute gradient updates using the global model and their local data, and then share the updates with the server. The server aggregates the updates using some aggregation algorithm, such as coordinate-wise average, and updates the global model using this aggregate and stochastic gradient descent algorithm. This process continues until the global model converges. For example, the model achieves the desired classification performance on a given task. Many companies have already adopted federated learning for different purposes. For example, the next word prediction feature of Google's keyboard uses federated learning, and IBM uses federated learning for medical image diagnosis. Now, federated learning is a distributed system, which means its collaborating clients cannot be trusted. That is, some clients can be malicious and try to jeopardize the global model. For instance, it has been shown that even a single malicious client can completely manipulate the simple averaging-based federated learning. So to address the issue of malicious clients in FL, literature has introduced robust aggregation algorithms that reduce the effect of the malicious clients updates on the global model. Examples of such robust aggregations include coordinate-wise median and trimmed mean. The motivation of our work is as follows. As we will show, the previous poisoning attacks on federated learning give a false sense of security against malicious clients. This can mislead the future designs of robust FL algorithms. Hence, our aim is to understand the true threat of poisoning to Byzantine robust federated learning algorithms and understand what are the fundamental design flaws in these defenses. Learning from these flaws, our goal is to design defenses with more principled guarantees. For example, design defenses with the more desired guarantees on filtering of malicious updates instead of the convergence guarantees in non-convex machine learning settings. Now we discuss our poisoning attacks first. In our work, we focus on untargeted poisoning, where the adversary's aim is to force the global model to misclassify all the test inputs. We focus on model poisoning attacks, where the adversary is allowed to directly manipulate the gradient updates of malicious clients. Note that this is different from data poisoning attacks in FL, where the adversary can only manipulate the data on malicious clients' devices. We assume that this adversary compromises less than 50% of total FL clients, because otherwise the poisoning attacks become trivial. In terms of adversary's knowledge, first we assume that the adversary has some data from benign data distribution, and next we consider the two most important dimensions of adversary's knowledge in FL: knowledge of the gradient updates of benign clients, and knowledge of the server's aggregation algorithm. We consider all the four possibilities combining these two dimensions and note that these possibilities encompass all of the possible untargeted model poisoning threats in federated learning. Note that our work is the first to give a general framework that can be used to systematically design both aggregation tailored and aggregation agnostic attacks. The intuition behind our attacks is to first identify the space of benign updates and then find the malicious updates that maximize the distance between the benign and malicious aggregates. So how to design the space of benign updates is an important question to answer. In case of aggregation tailored attacks, the constraints of the aggregation algorithm itself decide the space of benign updates, while in case of aggregation agnostic attacks, the benign updates that the adversary knows decide the overall space of the benign updates. Sorry. Adversary can obtain such benign updates using the data she has from the benign data distribution. Now let's quickly look at an overview of our attacks. Consider the space of benign updates. Now we first compute a benign aggregate, which is denoted by delta BA, and then perturb this benign aggregate in a pre-specified malicious direction to obtain the malicious update, which is denoted by delta M1. We call such malicious direction a perturbation vector. Next, we compute the corresponding malicious aggregate denoted by delta MA1. Then we keep on increasing the total perturbation used to compute the malicious update delta M until we maximize the distance between malicious and benign aggregates. That is, we maximize the distance between delta BA and delta MA in the figure. Note that very high perturbations can lead to easy filtering of malicious updates. And on the other hand, very small perturbations can lead to very suboptimal poisoning attacks, as shown. Therefore, we give an efficient algorithm that adjusts the scaling factor gamma of the perturbation vector and computes an optimal perturbation to the benign aggregate to compute malicious update. Next, we formalize our general attack framework. We formulate our model poisoning attacks as an optimization problem as shown. For the details of the components of the framework, please check the main paper. As stated in our attacks overview, for any type of attack and aggregation, our goal is to find the combination of perturbation vector delta P and its scaling factor gamma, which maximizes the distance between benign and malicious aggregates. However, we show that simultaneously optimizing delta P and gamma is computationally expensive. Hence, we fix the perturbation vector delta P and only optimize the scaling factor gamma. This gives us our final framework formulation as shown. Theoretically, there can be infinitely many possibilities of malicious directions or perturbation vectors, but for brevity, we experiment with only 3 perturbation vectors in our work and show that these perturbation vectors have significant attack impact. So these perturbation vectors are inverse unit vector, inverse standard deviation, and inverse sign vector. It is worth emphasizing that we chose these 3 out of many that we experimented with in our initial explorations. We now discuss aggregation tailored attacks on multi-chrome aggregation algorithm, which is a state-of-the-art aggregation algorithm with strong convergence guarantees in the presence of malicious clients. Multichrome is based on geometric median. It first filters malicious updates to compute a selection set and then computes the average of the updates in the selection set as its final aggregate. The intuition behind our attack is to maximize the perturbation to a benign aggregate while also ensuring that all of the malicious updates are selected by multichrome. So now let's plug multichrome in our general attack optimization as shown. Then based on our intuition of the attack on multichrome, we can simplify the optimization as highlighted in the box. Note that this attack optimization both maximizes the impact of malicious updates and minimizes the impact of benign updates. This is because as the number of updates are fixed in any given round, when we maximize the number of malicious updates, we implicitly minimize the number of benign updates. Next, we'll discuss one of our 2 aggregation agnostic attacks. These attacks basically differ in the way we define the space of benign updates. Recall that the benign updates space in case of aggregation agnostic attacks, it is decided by the benign updates that the adversary knows. For our first attack called min-max attack, we define the space of benign updates such that the distance of any update within the space, including that of any malicious update, from any other update is upper bounded by the maximum distance between any 2 of the available benign updates. This can be formalized as shown. Here, the left-hand side shows the maximum distance between malicious and benign updates. Note that as before, malicious update here is computed by perturbing the benign aggregate using a perturbation vector. While the right-hand side of the formulation shows the maximum distance between any 2 of the benign updates available to the adversary. Next, we discuss evaluations of our attacks. We extensively evaluate our attacks across 7 aggregation algorithms. We consider both IID and non-IID client datasets and both cross-device and cross-silo federated learning settings. We compare our attacks with the state-of-the-art attacks for all of the 4 threat models discussed before. Note that for this table, we consider 20% federated learning clients to be malicious. Finally, we compare with the state-of-the-art aggregation tailored attack FANG and the state-of-the-art aggregation agnostic attack little is enough, that is LIE in short. We introduce attacks impact as the measurement metric. Attack impact captures the reduction that the attack incurs in accuracy of the global model compared to the corresponding no attack baseline. Note that the higher the attack impact, the stronger the attack. As we can observe in the given results, that for both CIFA-10 and FEMNIST, our AGR tailored attacks have significantly higher impact compared to the state-of-the-art FANG attacks across all the threat models. Similar to the aggregation tailored attacks, our AGR-agnostic attacks have significantly higher impacts compared to the state-of-the-art LIE attacks across all of the threat models. For more details on the comparison and reasoning behind the superiority of our attacks, please check the main paper. Next, we discuss our defense mechanism. Our state-of-the-art strong model poisoning attacks clearly motivate the need for stronger defenses against poisoning attacks. Therefore, we introduce a robust aggregation algorithm or a defense called divide and conquer, or DNC in short. The intuition behind our defense is to use the power of principal component analysis in detecting outliers. Principal component analysis has complexity of ODQ, where D is the input's dimensionality, hence it is prohibitively expensive if directly applied to the high dimensional gradients which are common in federated learning. Hence, for dimensionality reduction, DNC first samples a randomly generated fixed set of gradient dimensions from all of the collected gradients. The DNC then computes the principal component of the subsampled set of gradients, that is, computes the direction along which these gradients have maximum variance. DNC then projects all the gradients along the principal component direction. Then it computes the mean of these projections as shown, and finally removes those gradients with the farthest projections from the mean as shown. We prove that DNC provides strong guarantees on filtering of malicious updates in IID federated learning settings. As we discuss in the paper, filtering is the more desired robustness criteria than convergence guarantees, which is generally followed in previous works. This is because convergence guarantees in non-convex machine learning settings can be elusive. Next, we compare our DNC defense with all of the previous defenses using our attack impact metric. In the table, each column corresponds to an attack, and each cell in the column parentheses show attack impact for the most robust of the existing applications against the attack. Note that the lower the attack impact, the stronger the defense. The comparison shown here is for IID federated learning settings. We note that DNC clearly outperforms all of the previous defenses. Please check the paper for more comparison and detailed discussions on the reasons behind superiority of DNC. To summarize, in this work, we gave a general optimization framework that allows to design strong model poisoning attacks against any robust aggregation algorithm for federated learning. We also introduced a novel concept of perturbation vectors, which significantly boosts poisoning attack efficacy. We are the first to systematically study all the possible untargeted model poisoning threats in federated learning. The direct implication of our state-of-the-art attacks is that existing robust aggregation algorithms for federated learning are far more susceptible to poisoning than previously thought. Motivated by the shortcomings of previous defenses, we propose a new defense called divide and conquer based on the principal component analysis and show that DNC provides state-of-the-art robustness in IID federated learning settings. Finally, we evaluate our state-of-the-art DNC defense for non-IID FEMNIST dataset with 20% malicious clients using existing and our state-of-the-art attacks. We observe that even DNC cannot defend against our strong model poisoning attacks in such non-IID settings. This is primarily because of the large variance in the gradient updates in non-IID settings. We note that defending against the strong poisoning attacks in extremely non-IID settings, such as that of FEMNIST, is currently an open problem in federated learning research and an impactful avenue for future work. Thank you for listening to our talk, and please check and play with the code that we have released in the link of the presentation.